Hello everyone. We are starting yet another video series for Nanoelectronics, and in this set of video series we shall basically cover the sixth module. So far in the fifth modules we have covered a number of effects. In fact, it was all about the behavior of nanostructures to electric field and magnetic field. We studied various types of transportation, right? Parallel transport and perpendicular transport. We are taking all these concepts and we are thinking about designing electronic devices based on nanostructures. And in the sixth module, we shall focus on the electronic devices. Let's see what does your syllabus say. So according to your syllabus, we shall be covering MODFETs, HBT, the heterojunction bipolar transistors. We have already seen resonant tunneling effect in the previous module, and we shall see various devices based on resonant tunneling effect, the resonant tunneling diodes and transistors, as well as the hot electron transistors. We have seen hot electron effect. We shall study the transistor based on that. Again, we have familiarized with a Coulomb blockade effect. We shall see the single electron transistors based on Coulomb blockade effect. That is the first section of our module in sixth module. Later, we shall see various optical devices based on nanostructures. So again, to cover the syllabus, basically I have a major part was done by referring this textbook Nanotechnology for Microelectronics and Optoelectronics by J.M. Martinez-Duarte. Let's get started. Well, today we know that silicon technology has been seeing a tremendous growth in the sense of high level of circuit integration. This circuit integration cannot be achieved or cannot be even dreamed if we couldn't develop the third and fifth semiconductor compounds. So it is this third and fifth semiconductor compounds which has aided the circuit integration in our semiconductor technology today. Now, why is it that the third and fifth devices shows this many advantages? What are those advantages? Number one is the extremely high carrier mobility. In fact, the carrier mobility of various third and fifth compounds, say gallium arsenide, it's about one order of magnitude higher than that of silicon. It's a pretty huge value. Another thing, how is it possible for them to have such extreme mobilities? It's because of the low effective mass of the electrons. So these properties of the third, fifth compounds has helped them greatly to find a strong position in the silicon industry today. One such very important device is the MODFET, the modulation doped field effect transistors. Now, this is nothing new to you. We have already discussed or studied the modulation doped quantum heterostructures based on the aluminum gallium arsenide and gallium arsenide interfaces. It's just that. So MODFETs are based on the modulation doped quantum heterostructures, and a very interesting property of this MODFET is that they can work up to very high frequencies because of their very high carrier mobilities. And it was also observed that in fact the cutoff frequency of these MODFETs was much higher than that of silicon based MODFETs. We are familiar with silicon based MODFETs, right? MOSFET. So the MODFETs MODFET had cutoff frequency which was much higher than the conventional MOSFET. What more do we need? Let's see that graphically. See, in this graph we can see a plot of the operating frequency in y-axis and the gate length in the x-axis. What are the things that we can quickly observe from this graph? Number one, see, we have the silicon based MOSFETs here and the various HEMT devices. Okay, this HEMT devices, high electron mobility transistors, these are nothing but MODFET. HEMT is another name for MODFETs. Why? because of the extremely high electron mobility. Hence the name high electron mobility transistors, HEMT. So HEMT and MODFET, they are the same. Okay, coming back. So we have the silicon based MOSFET here and the HEMT devices. We can easily see that the operating frequency of the HEMT devices is much larger than that of the silicon device, silicon MOSFET. That is one important thing that you can observe. Another thing that you can observe is that as the gate length is reducing, as the gate length reduces, the operating frequency is in fact increasing. Whatever be your device, whether it be a silicon MOSFET, whether it be a MESFET, HEMT devices, whatever be your devices, as the gate length is reduced, their operation frequency is increasing. And finally, you can note that we have different HEMT devices: aluminum gallium arsenide, aluminum gallium arsenide, gallium indium arsenide, and aluminum indium arsenide, gallium indium arsenide. Of these three HEMT devices shown, the indium based HEMT devices, aluminum indium arsenide and indium gallium arsenide based HEMT devices have shown the maximum operating frequency. So these were the things that we could interpret from this graph. In fact, see, this graph was plotted at a temperature 300 Kelvin, which means, yeah, your room temperature. If your temperature was reduced to about 0 Kelvin, you can see that these frequencies could be much higher, right? So MODFETs or HEMT devices are capable of operating at extremely high frequencies because of the extreme mobility of electrons. Well, this quantum heterostructures, they are not just limited to FETs. And in FETs, we basically consider the parallel kind of movement, parallel transport. We also have this quantum heterostructures affecting the perpendicular transport in our heterostructure interfaces. And the operation of such transistors is based on the application of a voltage difference to the emitter, base and collector, just like our BJTs. Such structures are heterostructure bipolar transistors, the HBTs. Again, this is nothing which is very unfamiliar to you. They are nothing but the junctions of aluminum gallium arsenide and gallium arsenide, or we have the silicon germanium junctions. So we also have the heterostructure bipolar transistors, which are based on the aluminum gallium arsenide junctions. We shall also see various devices, right? We have seen how resonant tunneling occurs in perpendicular transport, right? So based on that resonant tunneling effect, we have the resonant tunneling diodes as well as the resonant tunneling transistors. And transistors based on your hot electron effect are the hot electron transistors. And we have seen that as we are reducing the size of our devices in the nanometric range, even a single electron can contribute greatly to their electrical and optical properties. We have seen the Coulomb blockade effect, and based on that you have the single electron transistors. And later we shall see the optical behavior of nanostructures too. So I hope I could just give you a brief idea about what we shall face in this module. Let's get started with our first electronic device, the modulation doped field effect transistors, or the MODFET. So here, in the case of MODFET or even in the case of HBTs, we shall consider A very conventional example, the aluminum gallium arsenide and gallium arsenide interface. So we have seen that a potential well for electrons is formed at the aluminum gallium arsenide and gallium arsenide heterojunction, which is in fact due to their reduced dimension. And this in fact resulted in quantified energy levels for the electrons, for the electron energy, right? Now, we have two types of transport, right? The parallel and the perpendicular. Parallel transport occurs when your electron moves parallel to the interface, and perpendicular transport when your electron moves through your barrier or perpendicular to your interface. When we studied parallel transport, we have seen that when the electron motion was in parallel to the interface, the electrons was in fact considered as free particles, right? And in such a case, the mobility of the electrons can be extremely high. Why? Why is that so? See, the electrons originally originated from the aluminum gallium arsenide layer, right? And then they were transferred to the undoped gallium arsenide layer. In fact, since the gallium arsenide layer was undoped, there are no impurity scattering taking place in the gallium arsenide region, right? And because of this reason, this very solid reason, the electrons could manage to get extremely high mobility in the gallium arsenide region. Hence the name high electron mobility transistors. And since it was based on the modulation doping of heterostructures, they also got the name modulation doped field effect transistors. Now, how does it become a field effect transistors? Because see, they are in fact controlled by the electric field that controls the motion of the electrons along the channel. So, modulation doping of aluminum gallium arsenide and gallium arsenide, and controlled by electric field, which gives them the name modulation doped field effect transistors, the MODFET. And also because of the high electron mobility, they also got the name HEMT. Now, these MODFETs were used for very high frequency applications, extremely high frequency applications. And in fact, they are a very good example of devices whose performance is based on the quantum behavior of electrons. See, because these electrons are in fact localized in a nanometric potential well, isn't it, in the gallium arsenide region, which is smaller than the electrons' de Broglie wavelength. So this is an excellent example for the performance based on quantum behavior of electrons. Now let's consider the field effect transistors based on the heterojunction. So this figure shows the cross-sectional representation of your typical MODFET. We have the source, the drain, and the gate electrons. And the energy band, or in fact not all the energy band, just the conduction band, if you remember, recollect from what we have learned earlier. The conduction band energy of the structure is also shown in the second figure. Right, here we have your quantum well. The triangular shaped quantum well is located at the interface of the intrinsic gallium arsenide. Gallium arsenide means it's an intrinsic or undoped gallium arsenide, and heavily doped N plus heavy N doped aluminum gallium arsenide. So at the interface of this we have the channel formation. Now see, one of the most important factor of this structure is in fact that the potential quantum well for the electrons is formed between the N-doped aluminum gallium arsenide and the undoped or the intrinsic gallium arsenide layer. In fact, we can also see that if you recollect again, if you recollect from what you have learned, The energy band gap of aluminum gallium arsenide is nearly 2.0, nearly 2 electron volt, and that of gallium arsenide is 1.41 electron volt. And because of this, see, the electrons which has been captured in this potential well has extremely high mobilities. And it is also observed that the typical width of this quantum well, which is in fact triangular shaped, right? It's a triangular shaped. See, in fact, the typical width is about 8 nanometer, which is thin enough for our electrons to behave as a two-dimensional semiconductor. Isn't it? The potential well a two-dimensional semiconductor. Why does the electrons in this section behave as a two-dimensional semiconductor? Because the triangular shaped quantum well is so thin that it's just about 8 nanometer, satisfying the conditions for a two-dimensional semiconductor. Well, in this structure we can also see, what are the things we can see? We have the intrinsic gallium arsenide substrate. We have the heavily doped aluminum gallium arsenide, and in between that we have a intrinsic aluminum gallium arsenide or a undoped aluminum gallium arsenide space, which is acting as a spacer. Now, the basic role of this aluminum gallium arsenide spacer, I hope you can see this. This spacer is to further separate the conducting electron channel from our N channel aluminum gallium arsenide and our intrinsic gallium arsenide. And this further increases the mobility of the electrons. So basically we take a spacer of width about, say, 50 Armstrong. It's so thin. Yeah, so I have summarized what we have said in the sofa. So if we take a look into this picture, we can see that it's almost similar to our MOSFET, right? We have the source, gate, drain, similar. Substrate, similar to MOSFET. Then what is different? It's the presence of the spacer. We had the silicon dioxide region there. We have a intrinsic aluminum gallium arsenide region here. And the materials are same. Or in fact, our MODFETs are very similar to MOSFET. Again, see here we have your quantum well formation, right? Or potential well formation. This is again similar to your potential well formed at the silicon dioxide interface, isn't it? In the case of MOSFET, we had the channel formation in the silicon dioxide interface. So again, there is a big similarity. And in the case of MODFET again, or HEMT again, the electron current is generated from the source to drain when a potential difference is applied to them. And you can modulate the current by introducing a voltage at the gate terminal. See, this is again the same thing what happens in the case of MOSFET. In the case of MODFET, we can again see that the saturation current depends upon the gate voltage and threshold voltage by this relation. Isn't this similar to MOSFET? Right? So, since this equation is also similar to that of a MOSFET, in fact their IV relationship of MODFET is similar to that of MOSFET. Right? So we can also observe here that for the performance of this MODFET at extremely high frequencies, we require one condition, that is the switching speed related to the electron transit time must be shorter. So if your MODFET want to have an excellent performance at extremely high frequencies, their switching speed must be improved. And how can that be improved? By reducing your transit time. This in fact result in the fact that your gate length, see, your gate length L must be as small as possible. Normally it's 100 nanometer. It must be as small as possible. If a gate length is very small, your electron transit time will be made shorter. Your switching speed will increase. Finally, producing a better performance of the MODFET devices. So that's it. And see, what makes this, whenever we are thinking about a device in the market, what makes them feasible? It's because of the very low noise device market. See, MODFETs have extreme high frequency performance along with very low noise, and they can work up to a frequency of about 100 gigahertz, which is a pretty huge frequency range. And as we have seen from a previous graph, we have new types of MODFETs being researched, which are the aluminum gallium arsenide and indium gallium arsenide heterostructures. So they have even better electron confinement, even better electron mobility, and they can take the MODFET industry further high. So basically the transconductance values of these devices are given. It's nearly 100, and the cutoff frequency is about 100 gigahertz, as we have said earlier, and the noise level is 2 decibel. So these are like in fact a kind of perfect values, which makes MODFET preferable for a huge number of applications. And today we have research going on even the silicon germanium based heterostructure based MODFETs. So conventionally we are familiar with the aluminum gallium arsenide and gallium arsenide MOSFET, but we have new kind of materials coming up in this industry. So that's about MODFETs. So we have seen one electronic structure, which is again based on a modulation doped heterostructure, which is MODFET. We saw why they got their name, HEMT. What are their basic properties, their structure, the energy band diagram, right? Their energy band diagram, their structure, their similarities with MOSFET, right? So these are the things that we discussed in this session. Please go through this and make sure you have got the concept very clear. Thank you.